morning, everyone. If you're online, please indicate that you're online. Just indicate that you're online. If you're online, please indicate that you're hearing me. We are active now. We are online. Please indicate your presence. Please indicate that you're online. Indicate that you're online. If you're active, please indicate. Please indicate that you're active so we can start. And please, if you have not shared the link, please share the link to other people to join. Do me a favor, share the link. Please share the link to people to join. Share the link to your different WhatsApp groups. Share. Also post them on your WhatsApp status. Please, let's share to our various departmental platforms. Okay, please, let's keep on sharing. Please, if you have shared, I would like you guys to comment in the comment section that you have shared. We shall be looking at some past questions in physics. Past question. In physics. And revelation question, things that you should expect in your exam. All right. We're going to start now. We are starting already. If you're active, please indicate. Please let's comment in the let me have your comment in the comment section if you are active. If you're active, please indicate. All right, we're going to start now. The first question we'll look at is under circular motion, and we are asked to state and explain Kepler's laws of planetary body. Kepler's laws of planetary body. The first question says, state Kepler's law of planetary body. For this, number 2 question says, derive the expression for the third law, for Kepler's third law. Then number 3, we're going to solve some problems under this after we are done. So state Kepler's law of planetary bodies. I'm going to just explain them. I will state them. I will explain first, then I will state. All right. By now, we all know what is planetary bodies. All right, like bodies that move in a circular path or in an elliptical orbit around the sun and all that, just like the Earth, the Moon, the stars, the Neptune, Mars. Okay, all of these are planetary bodies, right? Now, long before modern scientists came into existence and all that, people have this belief that planetary bodies move in a perfect cycle. They move in a perfect cycle, possibly maybe around the sun. They move in a perfect cycle around the sun. This was the belief that existed for years, that the Earth move around the sun. Even most of us we still believe that the Earth move around the sun in a perfect cycle. No, people have that belief. Not until modern scientists came and look at the story of how these planetary bodies actually move around what? The sun, or how they move and all that. Then there's a scientist called Johannes Kepler. Johannes Kepler, okay, who gave three fundamental laws that described the motion of this body around what? The sun. He gave three fundamental laws, and he called this law Kepler's what laws. This law described how these planetary bodies actually revolve, how they move around what? Sun. Okay? Now he gave three laws. The first law of Kepler, Kepler's first law, is called the law of orbit. The law of orbit. The second law is called the law. The first one is called the law of orbit, right? The second is called the law of area. The law of area. The third law is called the law of period. Period. It's called the law of period. We have the law of orbit, the law of area, the law of period. These are the Kepler's law. But I'm going to state them, then we'll look at their explanation one after the other. The first law is called the law of orbit. The law of Kepler's first law states that planets moves around the sun in an elliptical orbit, as the sun has one of the world focus. I repeat again, planets move around the sun in an elliptical orbit, as the sun has one of the focus, meaning that planets don't move in a perfect world circle around the sun. Like I explained, that people believe that planets move around the sun in a perfect circle. So Kepler came and gave the first law that contradicts that belief. The law is called the law of orbit. The planet actually move around the sun in an elliptical orbit, as the sun has one of the focus. Let me explain what an elliptical orbit is. Elliptical orbit is an orbit. It's called an orbit. The shape of this orbit is called an ellipse. From the word ellipsis. Ellipse is actually, don't mind my diagram, we're meant to have a diagram like this. Okay. All right. Like the shape of an egg and all that. Ellipse is actually a stretched circle. When you stretch a circle, either along the x-axis or along the y-axis, it forms what? It forms an ellipse. What I mean by that is that, let me show us first what a circle is. If I have a Cartesian diagram and every side here is equal, I have 4, I have 4, I have 4. If I'm to join all these points together, we are forming what? A circle. This is a perfect circle. A perfect circle is that circle that every point from the center have equal radius from each of these locus. Locus is that point where object can be located, right, around the circle. So if from here to here is 4, that means here is also 4, here is also 4, here is also 4, here is also 4. Now what happens if, let's say, we have a diagram like this, whereby we have here are 6, this point are 6, we have 4, we have what here 4. Definitely I cannot form a circle here because all the sides are not the same. So if I'm to connect all these dots, what we form? We form an ellipse. Okay, the shape of this ellipse called an elliptical orbit. Now, in an elliptical orbit, we have what we call the foci. We have the first foci here, F1, then a second foci here called what? F2. Are you there? For a circle, we don't have anything called foci. Reason because all the sides are what? Are the same. We don't have focus. We only have locus. Locus is along this part here. Above locus 1, We have locus 2, locus 3, locus 4. It is this locus that defines the circle. Now, every point from the center to this locus are what? They are all the same. Right there? But when it comes to an ellipse, when a circle is being stretched along the x-axis, like we saw, here we have 4 initially. But what happened is that we stretched it a little bit away. Like we added 2 units extra to this 4, making it was 6. So that gave us what? An ellipse. So this is what we call an elliptical orbit. This was what Kepler saw when he made his own research and found out that planetary bodies like the Earth, Neptune's, all those Mars, stars, and the rest actually revolve around the sun in an elliptical orbit, as the sun as one of the focus. Like I explained, that in an elliptical orbit, we have how many foci here? We have 2 foci. Right there? What Johannes was saying is that one of these foci here occupies what? The sun. We have the sun here. So the sun represents what? A foci. Alright? As the planetary bodies actually what? Revolve. They revolve. They revolve. They revolve. So this is what the first law is saying. It's called the law of orbit. That planets revolve around what? The sun. This is sun here, right? This is sun here. The mass of the sun is mx, right? Planets revolve around the sun. They revolve around the sun in an elliptical orbit, as the sun as one of the focus. This is what the first law is describing. Please, if you are active, please indicate that you are active so that we can proceed. Please, if you're active, please indicate that you're active. Please indicate that you're active. If you're active, please indicate. If you're active, indicate that you're active. If you are following, please indicate. Please let's indicate that we are following in the comment section. Now we have seen the first law, right? Which is called the law of orbit. Please, I need your comment. I need your comments. Let me know those who are following, please. If you are active, please indicate. Okay, so let's continue. Now we have seen the law of orbit, right? Which is called Kepler's first law. Please, from the comment section, indicate if you understand what I just mentioned. If you understand it, just indicate. Please, if you understand it, just indicate here. Okay, now the second law is called the law of area. The law of area, right? The law of area. But let me describe some things here. Don't forget that as this body here, let's say we have Earth, right? As Earth is revolving around the sun in this elliptical orbit. Okay. Now, whenever the Earth is far away from the sun, okay, the speed of the Earth is slower. The farther the distance between the Earth and the sun, the slower the speed of what? Of the Earth. All right. As this Earth is approaching the world, the sun, the speed increases because of what we call the force of what? Gravity. There is a force called force of gravity, according to um, Newton's laws of gravitational force, that says that the force of attraction between two masses, right? The force of attraction between two masses is proportional to the product of what? Of their mass, right? And also the force is what? Inverse proportional to the distance separating the two masses. I believe we all know this, right? We call this Newton's laws of what? Gravitation, or law of gravitation, not force, right? So we know that the more the the farther the distance, okay, the more the what? The force. As the distance is reduced, the force will what? Will increase. Meaning that as this Earth is approaching what? The sun, the force of attraction that will push the Earth to increase the speed of the Earth to move past the sun will also what? Increase. So this region here, we call this region the perihelion region. The perihelion region, which is the region where the Earth is close towards the sun. Then this region here is called the aphelion region. The aphelion what? Region. But this is not my concern in this topic. My concern is that as this Earth is approaching, the the more the distance between the sun and the Earth, the slower the speed of the Earth. So as this Earth is approaching the sun in this elliptical orbit, the more it's approaching, the more the speed will increase because of the force of attraction. There will be a force of a pull between what? The Earth and what? And the sun. That means that from this sun here to the Earth, we have what we call our radius, right? So from the Newton's laws of gravitation, we can say that the force of attraction is proportional to what? Mass of the sun, right? Times what? Mass of what? The Earth. Or we can use, let's use P to represent planets. Any planetary body. It can be the Earth, it can be this, it can be the moon, it can be the stars, it can be Neptune, it can be Mars, it can be, every other planet. So let's use the word P to represent what? The planetary world bodies. That as this body here is approaching the sun, the speed will increase, right? Because the lesser the distance, the more the force of attraction between the sun and the planetary body. So that means that the force of attraction is proportional to what? Mass of the sun times what? Mass of what? The planetary body, right? Okay. That same force is what? Inverse proportional to the square of the distance separating the sun and the planetary body. So from here, we can define the force as what? By the time we combine these two, if these two exist, this is equation 1, right? This is equation 2. By the time we combine these two forces, that means our force is then proportional to what? Mx times mp divided by what? Rho. Now, if I'm to take off this sign, what do? We have to introduce our constant. In this case, our constant is what? G. G mx mp over somebody over r squared. All right. I'm going to use this expression to derive the formula for the third law, which is called the law of period. So why explain, I will still come back to this law of period, all right? Because this is very important and all that. But just take note that the first law is called the law of orbit, that planet tends to move around the sun in an elliptical orbit as the sun represents one of the focus, as the sun is in one of the focus. So if the sun is here, planets tends to what? Move around the sun in an elliptical orbit, has the sun as one of the focus. This sun can either be here or be here. Sun cannot be here at this. It can't be here and at the same time also here, right? And the sun cannot be at the center. The principle, the law say that the sun must be found in what? In the focal point, in the focus of what? Of that elliptical what? Orbit, not at the center. Not at the center. The sun must be found here. That's what the first law of orbit is saying. The second law is called the law of what? Of area. The law of area. Now listen. The law of area. Number 2, the law of area. The law of area says equal area in equal time. Equal area is gotten in equal time. This is just the summary of the law of area. Let me draw a diagram again and explain what I mean by that. Then I will now give you the main law from your textbook. Listen, we now agree that the motion of planets forms what? An ellipse, right? Or they move in an elliptical orbit. Now, as the sun as one of the focus. So if the sun is somewhere here, right? I have the sun here. I have the sun here. Don't forget, this is my sun. Then we have our planetary what? Bodies, right? Revolving around what? The sun. Is that clear? Revolving around the sun. Now, what this law of area is saying that if this body here move from here, if the area cover from here to here, away from the sun, if the area could move from here to here, let's say it's covered in 1 month. In 1 month, okay? This is the area covered, let's say in 1 month, all right? That same area will be covered. Don't forget that let's say I have under the same planetary body here. Let me have here as point A and what? Point B. Let's have here as point C and point what? Point D. The distance, the area covered from here to here in 1 month is the same area covered from here to here. The same area. Are you guys seeing what I'm doing? The same area, this area here, is also covered from here to here in what again? In 1 month. Irrespective of the distance of between these 2 points here from what? From the sun. Now, what the law is saying is that if a planetary body move from what? From point A to B in 1 month, and away from the sun, if the same movement is taken from here to here in 1 month, that any value you have here in this area must be the same value you have here in the other area. So equal area gives what? Equal what? Is obtained in equal what? Time interval. Equal area is obtained in equal time interval. Don't forget that the reason why this part is somehow smaller is because away from the sun, the speed is what is minimal. The speed the body takes, this body here, this planetary body takes to move from point what? Point D to point C is not the same speed it takes to move from point A to what? To point B. Don't forget that the speed it takes to move from point A to B is faster, right? Is high compared to what? C to D. The reason being that at this point here, this planetary body here, right, is very close to the sun, closer to the sun. So because the distance between these bodies and the sun, okay, is very short. That means their speed will also be what? Be much. So the speed the body takes to move from point A to point B is high. but the speed it takes to move from point C to point D is what? Is very slow, or is low rather. But in as much as this speed here is high and this speed here is low, if it takes 1 month for this, let's say for the Earth, for instance, to move from point A to B, and it also takes 1 month to move from point C to D, what this law is saying that the value of the area covered here must be the same area covered here. That's the Kepler's law, the second law of Kepler. But let me state this for you. The law says equal areas in equal time, right? Please write, or a line segment joining. The law says that a line segment joining a planet and the sun sweeps out equal areas during equal interval of time. I repeat again, a line segment joining a planet and the sun, a line segment, right? That joins what? A planet and the sun. Are you following now? Sweep out equal area, generate equal area during equal interval of time. I hope this is clear. Meaning, if I have a stopwatch and I monitor how this planetary body move from point A to point B, let's say in 1 month, the same time will be covered to move from point C to what? Point D. Although the distance here looks smaller, but the distance here is what? Wider. Are you there, somebody? Now we are looking at the area covered. That the same area covered here must be the same area covered here. Okay? Don't forget that we call this region what? The perihelion, right? What we call here what? The aphelion, right? The aphelion. Okay, that is the second law. The second law. The second law. Okay. Now the third law of Kepler's third law is called the law of what? Period. What is period? Period is the time taken for a body to move to complete one word oscillation, meaning that if my planetary body is at point C and it moves from point C and returns back to point C, it has covered what? One period. And if we look at the Earth, for instance, the Earth makes 365 for days. That means that the Earth the Earth moves round the sun, and returns back to its position in how many days? 365 days for the Earth. For the Earth. Now, one good thing about Kepler is that it enables you to find the period obtained, or the time interval between what? The sun and what? And the Earth. If you can be able to generate the time interval between the sun and the Earth, you can be able to generate the time interval between the sun and other planets. That's one thing about Kepler's law. Because what I'm saying now, I'll be applying them in some calculations and we shall be seeing them. But the third law, let's look at the third law. I'm going to derive an expression, then I will state the third law. The third law is called the law of period. It's called the law of period. Let's look at this planetary body here. Let's say we have this, right? And we have our foci, F1, and we have what? F2, right? In mathematics, okay, we call this longer side the major axis. The major what? Axis. This is called the major axis. The major axis. The longer side. Why this side is called what? The minor what? Axis. Okay? Okay. Now, the major axis from this center here to this point is called A. From here to here is also called A. But from the shape, this becomes negative, right? From here to here, we call here what? Here is B, right? Here is B. Here is what? Minus B. So the major axis, if I'm to add up A plus A, that means this will be what? 2A. From here to here is A, from here to here is A. Then from here to here, which is A, we call it the semi-major what axis. From here, I repeat again, if from here to here is 2A, that means that from this point here, right, to this point is called what? A. Is that clear? And we call this what? Semi-major axis. Alright? Now, I say something before now that the first law, which is called the law of orbit, say that planet moves around, right? Around the sun in an elliptical orbit as the sun as one of the what? The focus, right? Meaning the sun is somewhere here, right? I have the sun here. We have the sun here. The sun is there. The sun is there. The sun has what we call the mass of the sun is represented as what? As ms. Let's say if I have my planetary body here, okay, planetary body here, okay, and let's represent this as what? As P, letter P. All right. Now don't forget that I say that as this body is approaching the sun, the speed will tend to increase. If this body is there, the speed at which the body will move, right, is slower compared to when the body is here. The more the body approaches for the sun, the more the force of gravity will increase. According to Newton's law of gravitation, that the force of attraction, right? Okay, the force of attraction between two masses, okay, is proportional to the product of what? Of their mass. And that same force is what? Inverse proportional to the square of the distance between them. That means that if I have my mass of the sun, and here I have the mass of what? The planet, right? And I have my distance of separation, okay? I can also connect it with this one here. If I have here as ns, and here's what? np. If I'm considering this and this, okay, that simply means that the distance between this and this will be what? Will be here, right? If I'm, let's say, if I have another particle here, if I have it here, the distance will be what? Will be r. Is that clear? It can also be here. Somebody, I can also connect this with this. Is that clear? Which is what? np. Okay. Now, okay, let me even ask a question. If I'm to consider this mass here, mass of this body here, with this mass here, which one will have a higher speed? Which one will move faster? Definitely it is because this other planetary body, right, is closer to what? To the sun. Like I said before, the closer these bodies to the sun, the faster their what? Their speed. The faster their speed. And what causes uh, the high speed experience is because of the force of gravity that tends to occur between the sun and what? And those planetary what? Bodies. Okay. But throughout this topic, I'll be using the Earth as an assumption or as a case study to derive the expression for the law of what? Of period. The law of period. I will not state the law. I will derive an expression. And from that expression, we will now look at what the law is actually saying. Now, look at this here. We have seen that there is a force of attraction between the between those planetary bodies, right? And what somebody and the sun and the sun. And we agree that please, if you are following, indicate that you are following. Please, if you are following, indicate that you are following. Please, from the comment section, please indicate. Are you guys following at all? Are you guys following at all? Now, listen. Now, the force of attraction, the force. I'm solving this now, the derive. From here, I will state the third law. The force of attraction between the sun and what? And the planetary body, right? What do you think that would be? We're going to call that Fg, which is what? From the formula, Newton's laws of gravitational uh, force. What do we say is the expression again? We say this what? Let me clear. Fg, right? Equals to what? G m1 m2 over what? R squared, right? Meaning that one of these mass will represent what? Mass of the sun, right? While the other will represent what? Mass of what? The planetary what? Body. Then divided by square of the distance between them. So I can choose this as a reference, or I can choose this as a reference, or I can choose this as a reference. Okay? All right. So if I'm saying that Fg is this, so from this diagram, our Fg becomes what? Yeah, that will give us G mx mp over what? Over r squared. Let me call this equation what one. What does this formula mean? That the force of attraction between the sun and the planetary body is what somebody gmx mp over what r squared. Just like we say gm1 m2, right? Now let's move on. I would like to clean this part so we can continue. Now listen, don't forget that whenever a body moves around a circle or around an elliptical orbit or around a sphere, there is always a force. There's always a force provided, okay, that causes the body to move. Look at this. Although we say that the force that causes the body to move, right, is the force of gravity. This force of gravity created a force called the centripetal force, an inward force that enables this body to move. So our Fg is what provided the centripetal force. If not, this body will not move in a circular path. So that means that since Fg provided a force called centripetal force, the centripetal force is an inward force that causes this body to move from one point to another. Don't forget that the sun is stagnant. All of these bodies there are revolving what? Around what? The sun. So the centripetal force is not is not with respect to the sun, but rather with respect to what? To the planetary what body. That means that I can say that since Fg provides what? Provides the centripetal force, right? The centripetal what? Force, which is what? Fc. Therefore, we are saying that Fg is equals to what? F what? Fc. What do we say is our Fg again? Fg we say is what? Gmx mp, right? Over what? Over r squared. Centripetal force we know is given as mv squared over what? R. This force is given as what? mv squared over r. But now the question is, this m here, will it be the mass of the sun or the mass of the planet? Definitely, this centripetal force here is only concerned for what? For the planetary world body. That means that the mass here will correspond to the mass of what? The planetary body, not that of the sun, because it is this body that is moving in this elliptical orbit. So that means our centripetal force here will then be what? mp, right? Mass mv squared over r. That will be what? mp v squared over what? Over r. Now let's move on. One of these can cancel one of these from here. mp can cancel mp. If mp cancelled mp from here, what do you think will be the result? Here we are left with what here? Gmx over what? R squared. Okay, also, one of these r, here I have r squared. Here I have r. One of these can also go with one of these. Here we are left with what here? R. All equals to what? V what? V squared. Don't forget that in circular motion, there is a relationship between linear speed and angular speed. Since this body is moving in a circular path, recall, don't forget, recall that linear speed is equals to what? Angular speed times what? Times radius times r. This is where the assumption comes in. The assumption of us considering, I've cancelled out mass of the planets. So that means that we're not going to be assuming that the distance we are considering is the distance of the sun to the what? To the earth. The earth is not a perfect sphere. The earth is like it's not really a perfect sphere, it's like an ovoid. Like, how will I do it? The earth is not circle. The earth is not a perfect sphere, right? So if we are looking at the sun representing standing at the middle, all right? If the sun is here and we have the earth here, so the distance between the sun and the earth is what? R. Am I communicating? But when it comes to an elliptical orbit, the distance between the center, the sun, right? The center here, and that of what? Let's say, okay, distance between the what's called the sun and our MP we use what R, right? But the distance between the center to this axis here is what? Is A. Is that clear, somebody? So if I'm to consider maybe the Earth, for instance, an assumption, we are looking at the Earth now as the planetary body, right? So that means I'm going to bring out a diagram, a sphere, but not a perfect sphere. Then the sun is here. I have the Earth here, right? I have the Earth here. Distance between the sun and the Earth is taken as R. That's where this R comes in. Although I would have just said, let's use A or B or anything. But let's look at this. If the sun is somewhere here, I don't know how to explain this because I don't want to go into the principle of eccentricity. Eccentricity. The when it comes to eccentricity, when eccentricity is greater than 1, we have a long elliptical orbit. When eccentricity is equals to what? 0, we're going to form a perfect what? A perfect circle. When the value of E is equals to what? 0, we have a perfect circle. Second semester mathematics, let me not go into that. There's a topic called conic section. When we talk about circle, talk about ellipse, talk about parabola, talk about hyperbola. Under ellipse, you'll be hearing things like eccentricity, which is the ratio of C over what? A. I won't go into this for now. But when the eccentricity E is equal to 0, it means that will form a perfect circle. But when it exceeds 1, it means it will form a long elliptical shape. All right? So the sun is almost the eccentricity of the Earth is almost close to 0, but not 0. That is why the shape is like a sphere, but not really a sphere. Are you there, somebody? Now, but just note that from here, V equals to what? Angular velocity times what? Radius. Exactly. Also, I hope you are aware that angular velocity is also defined as 2 pi over what? Period. Right? So I can put my value of my angular velocity here to form this. That means our V equals to what? What do we have at angular velocity? 2 pi r, right? Over what? Over period. We call this the orbit speed or orbit what? Velocity. The orbit speed or orbit velocity. So from here we have gotten our V to be what? 2 pi r over what? T. Then what we do is to put this value into this expression. Into that expression. Let's see what we are going to generate at the end of the day. I hope I can clean this part now. Please, if you have not shared this link, please share it to your classmates. Let's put this expression here. Therefore, what we have here today G, mass of the sun, right? Over what? Over radius, all equals to our V square. That will give us 2 pi r divided by T, all what? All squared. So from here we have our G mx over r, all equals to 2 pi will give us what? 4 pi squared. Then we have r squared, right? Divided by what? Our T squared. We are almost getting there. Now the next is to cross multiply. By the time we cross multiply this, 4 pi squared r squared times r will give us what? 4 pi r cubed, all equals to T squared times G mx give us G mx T squared. G mx T squared. Now let's see what we're going to do. Okay, now we say the third law is called the law of period. So I will look for a means to make my period to stand alone as the study of the formula. I will look for a means to make our period to stand alone as what? As the subject of what? The formula. Now, how do we make our period to stand as the subject of the formula? Is to divide both sides by what? G and x. Divide by what? G and x. Divide by what? G and x. So G and x can cancel G and x. We are left to what? Yeah? Period. All equals to what? 4 pi r cubed divided by what? By G and x. By G and x. Okay. All right. I hope you guys are following. Then let me use this small space here. Okay, I have to clean this. Okay, please take note. If you are following, please indicate from the comment section that you are following. Please indicate that you are following. Please indicate. Please indicate that you are following. Someone said start from the beginning. That means you came in very late. You came in very late. We are not starting from the beginning. Later you can go back to the class, to the video and watch. All right. Oh, okay. All right. Please indicate from the comment section if you are still with us. Okay. So let's proceed. Let's proceed. Let's proceed. Let's proceed. So from here, we have that. We can also express this as t squared equals 4 pi over g mx, all multiply with what? R1 cube. 4 pi gmx, all multiply with r cube. I just have to factor out r cube here. So this is the third law. The third law. Kepler's third law. This law says that the square of the period is proportional to the cube of what? The distance between the sun and the planetary bodies. I repeat again. This law states that the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. It's called the law of squared. The law says that, I repeat again, the square of the orbital period, the square of the orbital period. Let me write on the board. The square of the orbital period, which is our capital T, is proportional or is directly proportional to the cube of the semi-major axis. to the cube of the semi-major axis of its orbit. Of its what? Orbit. Of its orbit. Okay, this is the proof here. Now, meaning that the square of the orbital period, which is this, is what? That is proportional to the what? To the cube of the semi-major axis. If this is proportional to this, that means this becomes a constant. What we are saying here is that our t square is proportional to what? Somebody? Cube of what? The cube of the semi-major axis of its orbital of its orbit. So this is what the third law is actually saying. I have my t square, I have what? My r cube. That t square is proportional to what? To the cube of this orbital semi-major axis, okay, of its orbit. Okay, so please take note of this. This expression you are seeing here is a constant. Hope you are aware. If we are saying that this is proportional to this, like for example, if I have y equals to what? Mx, right? This means that y is what? Proportional to what? To x. So m represents what? The slope, right? Or the constant. Exactly. So if we are saying that a is proportional to what? To b, that means our a is equals to what? kb. Is that clear, somebody? So if we are saying that t square is what? Proportional to what? r cube, that means our constant, our constant, which is what? K, is equals to what? 4 pi divided by what? G m what? X. We call this the Kepler's constant. The Kepler's what? Constant. This is called the Kepler's constant. Please take note. The Kepler's constant says what? 4 pi divided by what? G mx. So take note of this expression. Now I want to show us something very important. I hope I can clean this part. If we are saying, note that, if we are saying that t square is proportional to what? R cube, right? And we have to take off this sign. What do we do? Is to introduce a constant. Our constant is actually this, right? So k r what? R cube. That means our k is equals to what? T square over what? R cube. Are you guys following? By the time we divide both sides by what? By R cube. So just to find k, if t square is proportional to what? R cube, this is a direct relationship, right? As R cube increase, t square will also increase, right? Or as your distance between the sun and those planetary bodies increases, the period will also increase. Is that clear, somebody? Okay, by factor of what? Of 3, a factor of 2 here. So that means that here we have t square equals to k r cube. Then k equals to t square over what? R cube. Therefore, that means that my t1 squared over what? T2 squared is equals to what? T2 squared over what? Sorry. This implies that if my k is this, that simply means T1 squared over R1 cube is equals to T2 squared over what? R2 cube is equals to what? T3 squared over what? R3 cube. Take note of this. Take note of this. T1 squared over R13. If our k equals to T squared over what? R cube. So that means that T1 squared over what? R1 cube equals to T2 squared over what? R2 cube equals to T3 squared over R3 cube. Please take note of this. Now let's solve one or two questions under this and see how we can apply this question, these laws. Let's solve one or two problems under this. Okay, we have a question that says that, please, if you are with me, say you are with me. If you are with us, please indicate that you are with us. If you are active, please indicate that you are active. If you are active, please indicate that you are active. Please pardon me a little. Let me get the question out. Sorry, let me get the question. Okay, I've seen a question here. I want us to look at together. Hello guys, are you guys active? The network is very bad. Network is very bad. This is serious. I'm so sorry for that uh, network issue that just occurred a few minutes ago. I have a question here that says that the mean distance between the Earth and the sun is, excuse me, is 2.287 times 10 to the power 11. What is, sorry, the mean distance between the Earth and the sun is 1.5 times 10 to the power 11 meter. The mean distance between the sun and Mars. Mars is on. Hello guys, are you guys active? Sorry for the network issue. Are you guys still active? Please, if you're active, indicate that you are active. So sorry for the network disturbance. If you're active, please indicate that you are active. If you're active, please indicate that you are active. If you're active, please indicate that you are active. Okay, let's look at this question. Then we move into something else. I think we have dwelled much on this. Then we'll solve one other question in circular motion. The mean distance between the Earth and the Sun is 1.5 meter. Between the Earth and the Sun is 1.5 meter. The mean distance between the Sun and the Mars is 2.87 times 10 power 11 meter. Between the Earth and the Sun is this 1.5 times 10 power 11 meter. Between the Sun and the Mars is 2.287 times 10 power 11 meter. What is the period of mass around the Sun? The period of mass around what? The Sun in the Earth days. Now, this is just what I mean. Let's see if I have the Sun here, and I have, let's say we have it to be mass. Mean distance between the Sun, between the Earth and the Sun is this. Okay, so here we have the Earth. And here we have, let's say we have the mass. If this is the Earth, let me use the Earth, this is the mass here. So both bodies will form an elliptical shape, around the sun. They will form elliptical shape around what? The sun. Likewise, these two around the sun. Is that clear? Then this is the sun. This is our sun. This is the mass of the sun. This is the mass of the Earth. Is that clear? So between the Earth, then this is the mass of the mass given to, or this is the mass. If this is our Earth, let me use it as Earth, and this is our mass. So distance between the mass, the sun, and the Earth is R1, which is given as 1.5 times 10^11 meter, right? Distance between the sun and the mass is given as 2.287 times 10^11. Then we are asked to find the period of the mass. So from here we can say that let R1 rather, be the distance between the sun and the Earth, which is what? 1.5 times 10^11 meter. Then let R2 be the distance between the sun and the mass, which is about 2.287 times 10^11. Then we also find the period of the mass, meaning I'm looking for our T2. Then period of the Earth should be 365 days. It takes 365 days for the Earth to move around what? The sun. Period means the time taken to complete one oscillation, right? So for the Earth, it's about 365 days. Is that clear? Now we are now asked to find the period of the mass, which is our T2. Don't forget that, recall, according to Kepler's third law of planetary bodies, that we say that period, right? The square of period is proportional to what? Cube of what? Of the distance of the planetary bodies from the what? From the sun. Is that clear? Now from here, we are going to let's use our capital letter R here to represent the distance. So from what we discussed, we say when you take off this sign, what do we have? We have our period squared equals to what? K R cube, right? So our constant, which is our Kepler's constant, is T squared over what? R cube, which is same as T1 squared over what? R1 cube equals to what? T2 squared over what? R2 cube. So I can use this expression to solve for our T2. Now let me just clean up this so I can solve here. So if we are saying that T squared 1 over R cube 1 is equals to T squared 2 over what? R what? Cube what? 2. I can put the values of my T1. Our T1 is 365 all squared, right? Divided by what? Let's look at what we have here. For our R1 is 1.5 times 10^11, all raised by 3, all equals to our T2 is unknown, so T2 squared is unknown, all divided by what? Our R2 is about 2.287 times 10^11, all what? All to the power of what? To the power of 3. Alright, so let's point our calculator to see what we're going to obtain at the end of the whole thing. Just excuse me a little. Let's punch our calculator to see what we're going to obtain at the end of everything. Okay, or we can just make our t squared, our t2 all squared to stand alone as the subject of the formula to stand alone. If I'm to make my t squared as subject of the formula, so what do we do? Here become t squared 2, right, equals to what? I multiply this with this, then divide by this, right? So that will give me 365 all squared times 2.287 times 10 power 11 raised power 3, all divided by what? 1.5 times 10 power 11, all to the power of what? 3. Okay, let's see how we can evaluate this together from our calculator. I hope I can clear here now. So we have our t squared all squared is going to give us 365 squared. Let's see what we're going to have. This will give us a very big value. 365 squared is about 133,225 times 2.287 raised to the power of 3, 2.287, so 2.287, right? 2.287, 2.287 times 2.287. This is about 11.9619 times 10 to the power of, if I should find the cube of this, 2.287 per 3 means this in how many places? 3 places, right? I'm going to multiply this 11 by 3. That will give us times raised power 33, right? Then divided by, let's evaluate all and see what we're going to have at the end of the day. This will give us about 1.5 to the power of 3. 1.5 times 1.5 times 1.5 is about 3.375 times 10 to the power of 33. Is that clear? 11 times 3 is what? 33. So I guess this can go with this, right? We are now left with what? T squared 2. Let's multiply 133,225 times 11.9619. 9619. This is a very big value. Let me divide this result by 3.375. Okay, this will give us about 472,184.9267. So to find our T2, we have to find the square root of this number, right? Of 472,184.9267. All right. So let's find the root of that number. Square root of that number. Sorry, excuse me. Square root of 47. It's about 687. So my T2 is about 687.1571. So I can approximate this to be 687 days. 687 days. That means if the period of the sun, if the period the Earth takes to move around the sun is 365 days, that means it takes the mass to move around the sun in what? 687 days. Alright? So this has to apply the Kepler's third law of planetary world bodies. Okay. Now, I want to read out the laws now. Now we have seen the law. I've explained what the law represents. Please take note again that the first law, okay, which is called the law of orbit, right? It's a planet moves around what? The sun in an elliptical world orbit as the sun has focus, right? Number two is that the line joining the sun and the planet sweeps out equal area in equal time. And that number two is called the law of area, right? The law of area. The third law is the law of period, that says the square of the period of revolution of a planet are proportional to the cubes of their mean distance from the sun. All right. So these are the three laws of Kepler. Kepler's three laws. Now let's solve a question I saw in your past question that repeated itself in your textbook. Please, if you are with us, say you are with us. If you are active, please indicate that you are active. There's a question I want us to look at that I'm so sure that this question might appear in your exam, although I'm not 100% sure, or at least I'm 80% sure. So that means we have to take note of this question. Okay? All right, so let's look at this question. The question says a body of mass M attached. This question came out one certain year like that. Let me clean the box so we can learn. If you are active, please indicate that you are active. Indicate that you are active. Please indicate your present that you are active. If you're active, please indicate you're active. Now the question says that a body of mass M attached to the end of a long thread of length L suspended from a ceiling revolves in a horizontal cycle of radius r with constant velocity v. And if m equals to 2 gram, if m equals to 2 gram, length equals to 60 centimeter, if m equals to 2 gram, L is 60 centimeter, speed is 5 meter per second. Calculate the angle made by the revolving thread with the vertical. First question says calculate the angle made by the revolving thread with the vertical. Number two says obtain the period of oscillation from this system and show that the revolving mass swings like a simple pendulum when its angle of revolution becomes 0. Number three says calculate the period of oscillation of the simple pendulum. Okay, we're going to look at this question. Question says a body of mass M, the body of mass M, all right, of mass M attached to the end of a long thread of length L suspended from a ceiling revolves in a horizontal circle. That means that I have a mass, I have a body. This is a ceiling here. Then the body is here. Then the body is suspended from a ceiling, and this body moves in a circular path. The body revolves in a circular path, like a conical pendulum. Hey there. The body revolves in a circular path like what? A conical pendulum. A body is suspended, okay? Then the fan rotates. As the fan rotates, the body moves along what? Horizontal what? Path. It moves in a circular path, but along the horizontal component, right? The body revolves in horizontal circle. Okay, meaning there was circle created there by the what? By the body. But after the mass of the body is here. This is the body here, right? That revolves in a circular path. It revolves in a circular path horizontally. So that means that from this point here, we have our radius. Don't forget, the mass of the body is here, which is what? mg. This is the length of the thread, right? The length of the thread, which is our L. From here, we have our radius. Here, we have our height. Is that clear? Now, we are told that if mass is 2 gram, it means I'll convert gram to kilogram. If mass is 2 gram, right? And our distance, our R, we are told that R, okay, L is 60 centimeter, V is 5 meter per second, then R is given as 8 centimeter. We are now asked to find the angle made by the revolving thread, the angle made by the revolving what? Thread. Now, what do we do? Let's convert all our parameters. Please, if you are following, indicate that you are with us. If you are following, indicate that you are with us. We'll convert all the parameters to the appropriate standard. So 2 divided by, I will convert this to kilogram, meaning I will divide 2 by 1,000. That will give us about 0.002, right? Kilogram. Divide 60 by 100, we're going to have 0.6 meter. Divide 8 by 100, that will give us about 0.08 meter, right? Okay, and let's proceed further. Okay, now this is the diagram here. Let me repeat the diagram again. We are told that from the question, you have to pay attention to this question because this question is a kind of confusing. We are not told it's a conical pendulum. Please take note. We are told that a body of mass m attached to the end of a long thread L suspended from a ceiling revolves in a circular path of radius with a constant velocity. So this is our ceiling. Then we have the body here suspended. The body is suspended, right? So suspended. If the body is suspended, all right, the body will move in a circular path. Okay. All right. So from here we have our radius, which is R. We are told that the angle is along the vertical axis. Exactly. And there was a time we did a derivation of a formula using a conical pendulum. Right? So the height is given, this is our height, this is our length. Okay. Then we have a tensional force here. The weight of this body is here, which is mg. The weight is acting downward, right? All right. We can generate another angle here that is alternate to the given angle. Is that clear? This angle and this angle, they are the same. So their alternate angle, they are the same. Okay. This rope here, as long as if I have a mass suspended, there will be a force. There will be a force acting against a force trying to pull the body upward. That force is called the force of tension, tensional force, right? So the tensional force of the body will act this way. Is that clear? Tension is acting this way. Okay, so let's bring out, here we have this. This tensional force here can be resolved into 2 components. As long as we have the rope here, I have a rope and I have our x-axis, right? This is our arc, this is our length. Then we are told that we have our tensional force here, right? This is the tensional force here. Okay, and this is the mass of the body acting downward. This tensional force can be resolved into two components, which is Ty and what? And Ts. Please go through the previous class we had under conical pendulum. This is just the same thing, the same principle. All right. So here we have here to be what? Ty, and here to be what? Tx. Don't forget, this is our Ts, this is our what? Our Ty. Then the first question says, find the angle the rope makes with the vertical, meaning find theta. Find what? Theta. Now, the first thing we need to do is to resolve. We have seen that the angle of inclination is along the vertical axis. And we see that in vector resolution, because tension is a force, is a vector, I can resolve this vector into horizontal and what? Vertical. Horizontal is Ty, and vertical is what? Is Ts. Since the body is moving in a circular path, okay, horizontally, okay, that means the body is not accelerating upward. That means the sum of the two forces acting along the y-axis must balance towards each other. Okay, since the body is not accelerating horizontally, we have to note that, okay, let's note that first, that Tx is T sine theta. Ts is T sine theta because the angle is along the y-axis. If the angle is along the s-axis, Ts will be T cos theta. But because the angle is along the y-axis, it becomes T sine theta. Our Ty is what? Will become T cos what? Theta. Don't forget. Okay. Now, since the body is oscillating, is moving at a constant speed along the horizontal axis. So that means vertical acceleration is 0. So Ty must be equals to what? Tmg. These two forces must balance each other. The sum of the two forces must be equal to 0, meaning the sum of all these forces here along the y-axis. Okay, that will give us what? Our Ty minus what? Our mg equals to what? Ma, right? May. So since the body is not moving along the s-axis, so ay is 0. So mass times 0 is 0. That means our Ty minus mg is equals to what? 0. So Ty must be equals to what? Mg. So okay. So I will just come here and say, note that Ty is equals to what? Mg. Okay, but Ty is T cos theta. So T cos theta is equals to Mg. All right. So let's see what we're going to achieve. Let's just keep on solving. We have equation 1. Then also, look at this here. Tx is the horizontal force and is given as what? T sine theta. But don't forget that we are told that the body is moving in a circular path horizontally. It's moving this way horizontally, right? Why is it moving this way? Because Ts is a force that provided a certain force called the centripetal force. There's a force that causes the body to move along the horizontal axis, like we saw in Kepler's law, that when a body moves in a circular path, there's a force responsible. That force is called what? Centripetal force. But this force is provided by Ts. Okay. So since Ts provides the centripetal force called what? Fc. And we will also note that Ts is equals to what? Mv square over what? Over r. And that will give us what? Please take note. That will give us what we have here as our Ts is T sine theta, equals to mv square over r, right? Let's call this equation 1. Equation what? 2. I will then divide equation 2 with equation what? 1. Meaning I will divide equation 2 by equation 1. So T sine theta over T cos theta. I'm dividing this now with this, right? Dividing this with this, okay? Let's see what we're going to achieve at the end of the day. That will give us T sine theta over T cos theta, all equals to mv squared over r divided by what? By mg. Mv square. Our mv square, I've we divided this with what? With this, right? That gave us this. Then divide mv square divided by mg, and that will give us this, right? Okay. So t can go with t. Sin theta over cos theta is actually tan what? Tan theta equals to what? Mv squared over r times 1 over what? Mg. Mass can cancel mass from here. So we have tan theta all equals to what? V squared over what? Rg. So from here we can find the angle. We have to find the angle the uh the rope makes with the vertical, right? To find the angle, that will give us what? Our tan theta equals to our speed is what? 5 meters per second. We have 5. 5 what? 5 squared divided by our radius is given as 8 centimeter, which is same as 0.08. 0.08, right? Times gravity is 9.8. Please take G as 9.8 meter per second squared. That will give us 9.8, right? So let's see what we're going to achieve here. Here we have our tan theta equals 5 squared is 25 divided by 0.08 times 9.8. 0.08 times 9.8. 0.08 times 9.8 is about 0.784. 0.784. When you divide 25 rather, 25 divided by 0.0784, right? Sorry. Hello guys, I hope you are following. I want to find out something. Please, if you are following, indicate that you are following from the comment section. Okay, if you are following, please indicate that you are following. Come, let me check something. 25 divided by 0.784, which is this. Wow, shift and tan inverse of the result. Okay, all right, let's finish up. All right, so the next is to divide this, right? 25 divided by 0.784. That is about 31. 31.88778. So the next is to find the tan inverse of that. That's about 88. Let's take shift and tan inverse of 31.887. Sorry, excuse me. Shift and tan inverse of 31.8878 is about 88 points. So our theta here is about 88.2 degrees. So this is the angle we are looking for. So if you are given a question like this, you don't need to start deriving. I'm just teaching. Why I have to derive? Because I'm teaching. All you need to remember is just this formula here. Tan theta equals to V square over what? Rog. If you can remember this formula, just apply it and solve for your angle. The angle the rope makes with the y axis. Now the next question says, obtain the period of oscillation from this system. That's the first question. And show that the revolving mass swings like a simple pendulum when its angle of revolution becomes 0. Now the first, this is 2-in-1 question. It says obtain the period of what? revolution. Obtain it. The period of revolution. Let's see what we are going to have. The period of revolution. I've taught this before in the previous class. I don't know why I'm repeating it again. Maybe this question might appear in the exam. The period of revolution, the period of what? Revolution. That's our capital T, right? Now, how do we find it? How do we find this? From what we have here, from tan theta equals v square over what? Rg. Let me bring this here so I can maintain my space. From tan theta equals v square over what? Rg. Where this v represents the orbital speed, Abi. Okay, don't forget this speed, our v is equals to what? V is equals to w, angular velocity times radius. That's our v. Don't forget. Then from here, we also say that our v is also 2 pi r over what? Period. Because angular velocity represents 2 pi divided by period, then times r. I can put this value here. That will give us tan what? Tan theta equals to what? Our v is 2 pi r over period, all squared, right? Divided by what? Rg. So that will give us what? Tan theta equals 2 pi squared. 2 pi r squared will give us what? 4 pi squared r squared over what? T squared times 1 over what? Rg. Okay. Now, if we should have this, the value of r can cancel 1 of r here, right? And that will remain, we're going to be left with tan theta equals 4 pi squared r divided by what? T squared g. T squared g. Okay? T squared g. Alright. And we also note that. I hope I can clear here now. We also note that from the diagram we have, let me just repeat the diagram again for explanation. We have our mass here, right? We have our heights. We have the body moving in a circular path. Exactly. Then we have our radius. Exactly. Then we have our length and we have our angle called theta here. Okay. From here, I'll look for a means to eliminate this radius, this r here. Okay. To eliminate this r. Now we can decide to use opposite. So Katwa, opposite over what? Hypotenuse, right? Opposite over what? Hypotenuse. And that will give us what? Sine what? Sine theta. Recall that sine theta equals to what? What's our opposite here? R. What's the hypotenuse? L. So R over L. So I can cross multiply this, right? That will give us R equals to what? L sine what? L sine theta. So from here, I can put the value of my R here. That will give us our tan theta. Tan theta equals 4 pi squared in bracket. The value of R is what? Our R here is what? Is L sine theta. L sine theta, right? Divided by T square G. Also recall, don't forget that tan theta is sine theta over what? Cos theta. Tan theta equals what? Sine theta over what? Cos theta. So I can replace this with what? With this, right? And that will give us what? Sine theta over what? Cos theta. All equals to what? All equals to 4 pi square L sine theta divided by T square G. Okay, from here, sine can cancel sine from here. If sine should cancel sine from there, what is remaining is that should cancel that. What is remaining is 1 over cos theta equals to, we have 4 pi squared L, right, over T squared G. Our aim is to find our period, right? Don't forget that. By the time we cross multiply this, this is going to give us T squared G times 1 is T squared G. Then 4 pi square L times this gives us what? Equals to 4 pi square L, 4 pi square L cos theta. So our period then becomes 4 pi square L cos theta, all divided by what? G. So from here, my period becomes square root of 4 pi squared L cos theta divided by what? G. So here we have our period becomes root of 4 is what? Is 2. Root of pi square is pi. Square root of what? L cos theta divided by what? G. So this is the formula I'll be using to solve. This is what we are asked to derive. We say, what is the expression, right? Obtain the period of oscillation. Question says, obtain the period of what? Oscillation from this system. From this system. So this is it here. Then obtain. Let's obtain. So we can find the period here by substituting the value. T equals to 2 times 3.142. Okay. Then our length, the length is 60 centimeter, which is about 0.6, right? 0.6 cos. The angle we calculated was about 80 points. What was our angle? That was about 88.2 cos 88.2. Okay, let me bring this out again. Our period is 2 times 3.142 square root of, we have our length is 0.6 cos 88.2 divided by what? 9.8. So please point for me. Anything you have there should be the answer. That should be the answer. But the questions actually say that we should, excuse me, we should obtain the period of oscillation from this system. I think we are just to find the expression, not to even solve. When they say obtain, meaning just have to stop here. All they need is the derivation. If you don't understand what I just did tonight, go back to the first class. We have only done I've only done something on this under conical pendulum, and I took my time to explain it. All right. Okay, this is just like a refresh explanation for those of you who just join us. Okay, go back to my class. The first class we did under conical pendulum. I took my time to show us how we derive this. But if you still understand what we did here, that is still good and all that. So when I say obtain the period, the expression, it means I have to stop here. Don't need of calculating whatsoever. So that means that you have to learn this derivation because we might be asked to find this expression again in the exam. Now the next question that says, show that the revolving mass of a simple pendulum, okay, swings like a simple pendulum when the angle of revolution becomes what? 0. When the angle of revolution becomes 0, we have to show that the bulb will swing like a what? A simple what? Pendulum. We have to show it. How do we show it? And we are told that our theta is 0. I'll repeat the question again. Question said, show that the revolving mass swings like a simple pendulum, no longer like a conical pendulum. We want to show that it swings like a simple pendulum, but we are given a condition that when its angle of revolution becomes 0. When the angle of revolution becomes 0, when theta is equals to 0, that means that this becomes what? Period equals 2 pi square root of L cos what? Cos 0 divided by what? G. Is that clear? Okay, I guess let's point and see what then is cos 0. What then is cos 0? Cos 0 is 1. So cos 0 is 1. So period becomes what? 2 pi root of what? L over what? If cos 0 is 1 times L is what? Is L over G. This is what we are asked to show. This is the formula for finding period of a simple pendulum, which is T equals to 2 pi L over what? G. Don't forget, right? But if I have 2 pi L cos theta, that means this is a period of what? Of a conical pendulum. So to show that this is a period of simple pendulum, all we don't need to do is to put our theta as what? 0. And that will give us L over G. Okay. Now the next question, okay, that should be the last question. Now says calculate the period of oscillation of the simple pendulum. Calculate the period of what? Oscillation of the simple pendulum. Meaning that after we have converted this formula, this conical pendulum to simple pendulum, we have now to find the period of what? Oscillation of the simple pendulum. Meaning that I will use this formula to find the period. And that will give us period equals 2 pi root. Our length is about, excuse me, our length is about 60 centimeters. That is about 0.6 divided by 9.8. By the time we punch our calculator and find the entire value, we're going to have about 1.5 seconds. 1.5 what? Seconds. You can verify this, divide it by this, find the square root, then multiply with 2 pi. The answer should be about 1.5 per second. So this is all about this question. Either, please, if you are still following, indicate that you are following. If you are following, please indicate that you are following. Indicate that you are following. Please indicate that you are active. Indicate that you are active. Okay, someone said that in textbook they gave G as 10 gram. Fine. If you can use G as 10 gram, fine. That means there will be 10, Abi. Okay. Okay. But I'm just assuming, I assume G as 9.8, right? 9.8, 9.8. Okay. Now let's move down to something else. I hope my phone is still strong. Okay, my phone is strong enough to take us further. But please, if you have any question you want to ask, please quickly ask the question before we move to something else entirely. Please ask your question. Ask your question. If you have any question you want to ask, please ask your question. If you have any question you want to ask, please ask your question. Please do me a favor, guys. Do me a favor. Do me a favor. Share this link now to your different WhatsApp group. Please share. Please share. Please share. Okay? Please share it. Share it. Share it. Share it. Let's keep on sharing it. If you have shared it, indicate that you have shared from the comment section. Please indicate that you have shared it from the comment section. Indicate that you have shared it from the comment section. Indicate that you have shared it from the comment section. Someone is asking, sir, when are we ending? Okay, we are going to end very soon. All right, we're going to end very soon. We're going to end very soon. We're going to end the class very soon. So don't panic. Don't panic. Okay, I think we're going to end now because I was trying to glance through to see if there are other questions in your past question, but there is none in the past question. So what you guys will do for me is that you have to go through um, your textbook and see how you can solve some other examples from the textbook. But that remind me, we are having Night of Revelation. Night of Revelation, okay? Night of Revelation at EMI-BRAIN Tutorial College. So there will not be live class, live stream tomorrow being Sunday, right? Sunday night from 8 p.m. to 4 a.m. It's a physical class, not an online class, all right? But we'll look at how we can create a WhatsApp group for those that will likely join through our WhatsApp platform, all right? And the group will be shared across different EMI-BRAIN WhatsApp group. And if you are here, you want to join the WhatsApp group, okay, you can always reach out to me on WhatsApp through this number 0906311131961. This is my WhatsApp number. If you want to join the Night of Revelation, the class is starting tomorrow's night, which is Sunday night, right? From 8 p.m. to 4 a.m. And one thing about this Night of Revelation is it has never failed. This is over 10 years in this business, and every set we always have Night of Revelation, and it has never failed. I'm not guaranteeing you 100%. This is not IMSU exam question, or it's not UNN exam question, or it's not any school exam question. Either it's just a revelation and it has been working. We are only guaranteeing you about 80%, 80% of everything that will be taught during that class will appear in your exam, live and direct, because uh, we we have we have studied the pattern and through what we have been operating with, we've been able to see that it works and all that. So please, you can verify from other students who are in other levels, year two, year three, and all that. It works and all that. So please, if you are interested, if you are within Imo State, like those of you that attend Imo State University and you want to attend the Night of Revelation, just make sure you come on time. The class will start by 8 p.m. So as early as 7 p.m., be around. But once we start by 8 p.m., you'll be part of the class. So see you guys tomorrow at EMI-BRAIN Tutorial College. But meanwhile, we might likely have another live class, but that will be on Monday. On Monday, maybe possibly Monday morning. Monday morning, yeah, for just to touch one or two topics in physics and possibly in biology, because I learned that most of you are having biology and physics exam on Tuesday. So I'm likely come online on Monday to have a live class like this, but it won't be in the night because I'll be busy in the night. The night class will also extend to Monday night as well. So let's say Monday morning, I might be coming live on Monday morning for all underlevel science students. All right. So see you guys tomorrow. Thank you guys. Good night, everyone.